Hello and welcome to a very special edition of Maker Monday. Tonight we are doing something slightly different in that we're going to be taking a look at some tools that could completely change the way you think of your projects, specifically electronics projects. Tonight we're going to be looking at PCBX, which is a PCB manufacturing company, and some software which they're releasing to the community for use, which is an online EDA tool. So we're going to be taking a look at that EDA tool. We're going to be designing a circuit. We're going to do a board layout, and then we're going to place an order and see this process from end to end. So feel free to ask questions as we go along. I've done some looking at the EDA tool, but I'm coming at this from a new person's perspective. I've used things such as KiCad before, and I'm reasonably competent in using these bits of software. So I'd like to have a play with this tool as a beginner and see how this can benefit you in your projects. Welcome in, Stephen. You are very, very welcome. So this is going to be, as I say, a walkthrough. We can make this as interactive as possible. So if there's something somebody wants to ask in chat, we can go down a rabbit hole, or we can just go from the very, very beginning to work through the process of building a circuit. So first and foremost, what we're looking at tonight is electronics projects. Electronics projects are kind of the magic sprinkles on a project that can make it into something that is like the next level. It's all well and good having an awesome prop from a movie that you've made, or a particular object that has a defined function. But when you add electronics to these projects, it can just really top it off and make it look amazing. Now, that could be something as simple as lighting. It could be something such as automation. But it just gives that little extra. So typically, when you're working with electronics, you've got a couple of different ways that you can go about it. I remember when I was in school, and I learned about electronics, and this is a long time ago now. We would look at a textbook which would have a circuit diagram or a circuit schematic, and we would draw out a circuit diagram onto a piece of copper-clad board. In fact, I've got a piece of copper-clad board here. Give me 1 second. Let me grab something. In fact, I've got 2 different kinds. Let me see if I... Aha! Perfect. Perfect. Okay. So I would draw out a circuit with a special marker pen, and the pen that I would draw with, effectively the lines would make up the lines of a circuit. and I would have to draw like these little circles where the components would eventually be drilled and placed into the board. Now, there are two different types of board that most hobbyists will work with, and that is single or double-sided circuit boards. And I've got examples of both here. So this is an example of a single-sided copper-clad board. It's got a fiberglass sort of substrate that is essentially the strength of the board. And then you have the copper on the top, which has the conductivity that's going to conduct the electrical signals in your circuit. Oh, thank you. I appreciate it. There's lots of little gadgets that I've made, right, over the years, that can, you know, I can bring in as props. So appreciate that feedback. Thank you so much. So yes, this is a single-sided board. Sorry, this is a single-sided board, and this is the most common sort of circuit board that a hobbyist would use. It's easy. It's very uncomplicated. The other type is double-sided, and it means that you've doubled the area that you can actually use for running circuit traces. And that's really important when it comes to circuits which have lots of components on here. When it becomes busy and you need to route your traces, it can sometimes become really difficult. And what you can do is create what's called a via, which is a connection from one side of the circuit board to the other, transferring the signal over to the second side of the board, and it just gives you a lot of flexibility when it comes to making these types of circuits. Now, as you can see, I've got quite a few like circuit boards like this laying around. And as a hobbyist, there's really two main ways that I would make a circuit board. And the first and foremost would be to use a tank full of chemicals that eat away at the exposed copper. Now you can, very rudimentary, use a pen to draw your circuits, but there's all sorts of different tricks, from using a laser printer and using a toner transfer to using photosensitive film or photosensitive board and printing out a clear acetate and exposing the board that way. And you have to use these chemicals that are not particularly nice. And yeah, it's quite messy. If you get ferric chloride on your hands, it stains your hands yellow. And that's not the best thing to be having in contact with your skin. The other option is to use a CNC machine and CNC mill circuit boards out. We've got an example of a circuit board that I've made that was made on a CNC machine. This one happens to be a double-sided board. And this was made on a CNC machine. And the problem that I found with these sorts of things is trying to get the vias to work effectively and still keep a nice looking board, and trying to apply a solder mask and not expose, like get it all over the pads. It's hard, right? Jeffrey, thank you so much, and welcome in from Guatemala. Appreciate you. And thank you so much for the comments. So yes, there's many ways that you can make a circuit board at home. Now, why do I have so many circuit boards lying around unused? Well, the truth of the matter is that sending your designs off to a manufacturing company to have them made for you, professional quality, is a lot less stress. It's a lot cleaner. There's no nasty chemicals. And the result that you get is professional quality. What does professional quality look like? Well, professional quality looks like this. So you get circuit boards. I could never imagine myself making a circuit board as clean as this, with silk screen printing. Can I get the camera to focus? In fact, let me use this camera instead. Could I get silk screen printing? Come on, camera. This one doesn't want to focus now. There we go. Could I get silk screen printing like this at home? Hell no. Nice double-sided board with some excellent vias. So the quality of the board is better. The reliability of the board is better. So using a service like PCBX, to me, is a no-brainer, because I can outsource the manufacturing of these circuit boards to a company that does this for a living. It's their profession. You get excellent quality coming out of the production line. What does that mean for me? Well, less stress, no chemicals to clean up if I spill them. Those chemicals can be hazardous to your health. And the end result is more reliable. One of the things that I find with some of these, especially these boards that I have made that do not have a solder mask on them. One, you can see this one is tarnished. Can you see how it's not as shiny as the others? So the oils from my skin handling this and just exposing this to the elements has caused this to tarnish. And what that can do is it can degrade the connections of your components, leading to your circuit to fail in the future. With a professionally applied solder mask, that's less likely to happen. So, as I say, using a service like PCBX is a no-brainer, right? So, to make your circuit design, you need some sort of software to be able to create the drawing of how the components hang together. And you also need a piece of software to draw the traces onto a circuit board. And then we need to output them to a particular format and then send them off to a board manufacturer. Now, there's lots of different pieces of software available to do this. KiCad is probably one of the most well-known in the maker community, because it's open source, it's cross-platform, and it's something which, you know, it's feature-rich. It does a heck of a lot. It enables me to not only do double-sided boards, but I can design boards with, I don't know, up to 6-8 layers. And a professional board manufacturing company can take that data in and make a really, really high quality board. But you have to, one, get the software. You have to, which is free. You have to install it. You then have to learn it. And then you have to figure out not only how to design the schematic, the board layout, you then have to learn how to output the files. And there's lots of things that can go wrong along the way. So what we're going to look at tonight in PCBX design software is an online tool that you can use. It is all combined. It's all in one. And you can go seamlessly from the beginning of the workflow, which is the schematic design, right the way through to placing an order and not have an export in sight. So is there any questions from chat as I go along? Feel free to ask away, whether it's about a piece of project work that I've done here that I can delve deeper into. But we're going to spend the next hour and a half, 2 hours going into the design tool, and we're going to design a variant of a circuit that I've recently designed, which is a low voltage switch. I've designed a 4-channel 12 volt, I say 12 volt, low voltage home automation. It hooks into Home Assistant. It uses the Tasmotor firmware, and what it's going to enable me to do is to automate the lights that I have and clean up my cable management somewhat. I've already got automated lights as it is with a circuit that I built previously, but this could be improved, and I'm hoping that these modules that I'm building are going to do that. I'm going to install the module into a fake battery. So here is a real battery off the back of one of my lights. The circuit board is going to fit inside here, and this is going to slide into the back of my lights, and then we'll put a 12 volt feed in here, and then there'll be a 12 volt feed coming out to control the light. So this cleans up my cable management and makes it a lot easier to get live. Jeffrey, you mentioned my my lights. That's one of the electronics projects that I made, and it's gathering data from all of my socials. I do have a video on the YouTube channel showing how I made that. So feel free to take a look. But after we've finished with the stream. All right, let's get into it. So where do we need to start? So first thing we need to do is we need to go to PCBX. And you need to register, which is free. You can either use your Google credentials, or you can create an account. Now I'm going to butcher names. This is an occupational hazard of live streaming. How would you pronounce that? Varitek? I'm hoping I'm not butchering that. Asks, am I using a Rode mic? Yes, this is a Rode Wireless Go 2. And I am using OBS. Yes, it's a vanilla install of OBS. It's not Streamlabs OBS. It's straight OBS. So, and welcome in from Australia. So we're going to look at this PCB tool, the EDA. What does EDA stand for? Does anybody know? Answer in chat. What does EDA stand for? Well, it's not the European Defence Agency. Google's a friend. Electronics Design Automation. So it's an electronics design automation tool. So once we've logged into PCBX, we're going to go into the online EDA design tool, which is up here on the top left. And when we log in here for the first time, we've got a couple of different options. we have got some, we've got a hierarchy in the menu system for your files, any quotes that you might have submitted, and any orders that you've placed. So my quote, I believe that this is where you can submit not only a circuit board, but a bill of materials, or BOM, to the supplier, and they will quote you to fully manufacture the board. That's with all the components on it. It's delivered to your door and you're off to the races. No soldering iron, no solder paste, no more is needed beyond that point. Unless, well, I'd be interested to know if that includes through-hole devices. It's not a service I've used, but it is something I'm interested in taking a look at as to the advantages of leveraging a service like that. So, across the top here, we've got 3 options. One for a new design file, if you're creating a new one. We're going to do that in a second. We can import EDA files from PCBX, KiCad, AD, never heard of that one, unless that's an abbreviation for Atom, I think it is, and Eagle from Autodesk. You can import specific manufacturing files, also known as Gerber files, or the bill of materials. So you can bring all of that into this system. We've also got a bunch of example files here. One that caught my eye immediately was this Uno R3. Doing a lot of electronics projects, I like to use microcontrollers, because microcontrollers, you can program electronics functions in, as opposed to having analog circuits. For example, if you wanted an LED to flash, you could go old school and use some transistors, resistors, an LED, etc., to create a flashing circuit, maybe even a 555 timer chip. With something like a microcontroller, you can use a bit of software to say, turn an LED on for 5 seconds, turn it off for 5 seconds, etc. You can do the same thing, but in software. And that gives you a greater flexibility. And if you know how to do things both ways, more power to you. But it all depends upon your needs and requirements at the time. So let's go ahead and have a look at the example project here. The Arduino Uno R3 is the first Arduino that I worked on, and it brought me into the universe of microcontrollers, and it made it so accessible, which is what the Arduino project is all about. So the first time you load the EDA, we have a set of instructions, so yeah, beginner's guide, and it shows you how to choose symbols, placing components, moving symbols around. Let's have a look. What else we got? We got creating traces, switching to the PCB, and it goes through the process. And we may come back here because there's a chance we're going to get stuck. Totally possible we're going to get stuck, but we'll see. I'm not going to check don't show this again because I might find it useful later. So we are immediately greeted with what is known as a schematic. So this is a drawing of all of the electronic components that is used in an Arduino. And these little wires, these little green lines, these are traces. These are how the components fit together. And this is like, this is a logical block diagram, if you like, of how these components hook together. This is not intended to be how this is going to be laid out on a circuit board. So don't be tempted to try and do your layout here, because this is just literally connecting these components together in the correct sequence. One thing to note, and this is common for all EDA software, you'll notice that we've got lines crossing each other. Here's a good example of that. So we've got a component here, which is a USB connector. It goes through a fuse. It goes through some Resistors is the label. I'm guessing they're variable resistors. Words are failing me tonight. And you'll see this component Z1 goes down to an inductor L1. And there is a green dot. And there isn't a green dot here. Let's zoom in a little bit bigger, right? So you all can see this really good. So you've got this component here. What is the difference between this component here connecting to this inductor and this pin coming out, going straight out to ground or U ground? Well, the all important thing here is this dot. This dot signifies that this trace going down is connected to this trace going across, where this one is not. These are not electrically connected. So that's something really important to be aware of, because if you expect these wires to, if you're drawing a circuit diagram where you need these wires to connect, you need to make sure that the junction has a dot. And failing to do that, you're not going to get the results that you need. Okay, so you can see this is really complicated, and we're not going to delve into the whys and wherefores of an Uno R3, right? We just want to show you that the EDA software is capable of doing some really complex things. How complex? Well, let's have a look at the PCB. So here is the circuit board. This is what these board would look like if it was made. For example, let me grab an Uno R3. In fact, I've got one here in the background, or at least I did have. I think it's liberated itself. Oh no, I've got it. It's a slightly different chip, but it is the same. It's the same chip, but in a different form factor. Form factor meaning that the package is what's known as a DIP package, as opposed to, what is it? SOT? Is it some sort of SOT package here? So this component here is the controller, and this is the physical version of that. Right, so you've got your USB here, you've got your power jack, you've got your pins down the side, and if we switch back to the circuit board, you can see here is the USB, here is the power jack, here's the controller, here are the pins, and this is like a default setup. Oh, in fact, no, it is the same. It is using the same DIP package. I just realized. So you can do some really complex things. And one thing I really like about EDA software is that you have the ability to view your circuit in 3D. So by clicking the 3D button, what happens is we go into a 3D viewer. And because there's a lot to this circuit, it's taking a moment just to load up. It's bringing in all the components. And there is a 3D representation of an Uno R3. That's pretty cool, right? So you can see, before you ever make the circuit board, you can see it virtually on your screen. And that can save you a lot of hassles if you're looking at this and think, oh, actually, these components are too close, or, you know, aesthetically, something's not quite right. Then you can make changes and correct it. So I really like this. I really like this. And from a beginner's perspective, there's $0 entry, right? This is, as long as you have a connection to the internet, then you have access to this tool. And I know I'm not the biggest fan of subscription or online tools, because if your internet goes out, then you know you've lost access to a tool that you could potentially use on while your internet is out. However, in this instance, I want to showcase a tool that a maker can use coming into electronics and get access to the benefits as quickly as possible. Now, whether you migrate to using to something like KiCad, a fully fledged EDA software, I mean, it depends on what your requirements are and what your journey is. But ultimately, I think this is a really, really useful tool for a maker coming into electronics for the first time and being able to make high quality circuit boards from the get-go. Hey, CE Waffles! Welcome into stream. How you doing? How is your day going? We are currently looking at PCBX online EDA, and I've marked, just to be clear, EDA PCBX are sponsoring tonight's video. They've asked me to take a look at the EDA. So thank you so much, PCBX. Appreciate the support. While PCBX are supporting, they have said that I can give my feedback as I find it. So I've already provided PCBX with some feedback around the EDA, and changes have already been made. Improvements are already being made. Now, I want to be clear, this EDA is in a beta. All right, so it's currently in development. So this is early access to this tool. So it's not going to be perfect, but then again, what software is? So let's get in the meat and potatoes of this, shall we? Let's get going with designing a circuit from scratch. So we're going to create a new file. And we're going to get rid of this a moment. We'll come back to it, but so I'm going to change the name. So first of all, low voltage, right, single chan low, single channel low voltage. That's the name I'm going to give this file. So all I did there was to click the little pen tool and change the name just up here. You got it. We are go time. So there are common symbols that are used in circuits which you can grab from the left-hand control panel. There's all these public public devices that you can get access to, and you can search them by name. Or if you become a more advanced user and you create your own footprints and symbols, etc., then you can get them from here. That's beyond the scope of what this live stream is going to be about. We're going to use out-of-the-box functionality. Maybe we can go into more detailed stuff at a later time if that's something you guys want to hear about. But so one of the things, let's have a look at what we've got here. So we've got a standard menu system here that gives us access to all the usual tools that you would expect with a piece of software that you've installed on your computer. And the thing I like about this is being cross-platform, because as long as you've got a browser, this will work pretty much on anything from what I can see. I'll have to fire up a Linux box or something like that, just to see how this renders on a Linux browser. But there's no reason why you couldn't use Chromium on Linux and, you know, use this or use it on a Mac. But yeah, this appears to be cross-platform, which is an advantage of it being online. Okay, so we've got the standard sort of save, close, import, export. We got some edit tools for like rotating, redoing, undoing, aligning, and distributing components. That's pretty useful. That's some actually. I was working in KiCad today in a schematic, and I could have really done with having this feature in the schematic view. That was missing. So the fact that this is here in the schematic view, I really like that. The ability to lock and unlock components. So when you confirm that you want to stop something from being modified, you can select it and lock it. So that's cool. I like that. What else we got? We've got ability to zoom in and out, which we can use the like a mouse wheel to zoom in and out. Let's see. We can zoom fit. We can switch. This is something that's really useful. So mil, I believe, is a factor of inches, and millimeters is fractions or decimals in a metric scale. So there's two different scales, and that kind of flew me. And here in the UK, if we talk about it's 30 mil, very often, if it's not in an engineering term, what we're talking about is millimeters. We're metric in that sense. But the term mil, I believe, is an inch term. And you can actually switch between units, which I really like, the ability to switch backwards and forwards between these unit types. We've got grids, a grid type. We can use grid lines like that. Or you can use grid points. I always prefer grid points. That's something that I'm accustomed to. So whatever your preference is, you can select it. Tools, ERC, which is just an electronic. Is it electrical redundancy check? Essentially, it just checks out your circuit to make sure there's no faults in what you put together. That's not to say that you haven't done it wrong. You still need to build your circuit correctly, but I think it'll check for things like items on the board that don't have wires going to them, if they like pads that are just left hanging in midair. So they'll highlight that. Update PCB. This is how you push your design to the PCB designer. So we'll need to use that in a moment. Shortcut settings. Now this I like. An easy way to find shortcuts for how to use the tool. If you ever want to get proficient at any piece of software, learn shortcuts. The sooner you get to shortcuts, the faster you will be, because you're not hunting for a menu system. So the fact that not only can you see the shortcuts, but it appears that you can actually define your own by clicking in this box. So this is really cool. I'm liking what I am seeing here. Then we've got placement, and we've got this bar across the top here to help us placing components and wiring. So that's kind of like a duplication, but I like having both, because what I like as my preference may not be what you like. So okay. So let's get, as I say, into the meat and potatoes of this. I've got a series of screenshots of the circuit diagram that I created for my 4-channel controller. And we're scaling it down so it's a single channel. So let's go ahead and bring up the images of the schematic. Like so. Here it is down in the bottom corner, and we're going to start placing some components. So for this, we're using an ESP 12F module, I believe it is. Could be a 12E, but it's in the ESP8266 family of devices. Let me just show you one of these components. And let's bring this up on the microscope. Can I get this all in shot? This is one that's seen better days. Yeah, this is really small. So yeah, let me just hold it up to the camera instead. I was going to try and use the microscope, but I can't get far enough away. Right, so this is an ESP12F module, and we're going to use this as the brains of the circuit. So we need to have a minimal setup. So what do I mean by that? We need the fewest amount of components to make the ESP12 function. We need to be able to program it, which means we need to get it into its programming mode. And we need to be able to send data to it from a programming board. So this schematic over here is exactly that. This is the minimum that we need to make an ESP12F work. So let's go ahead. Let's put PCBX's tool to the test. Does it have these libraries? Does it have the components? Does it have the footprints that we need? Let's find out. So we're going to place our component by clicking Place Part. And we're presented with a part search option. And what this looks to be is a database. So we've got access to a database of components that PCBX as a manufacturer has access to. It looks like we've also got PDFs. So that's very interesting. All right, let's ESP12. Let's do a search for ESP12 and see what comes up. Instantly, we've got an ESP12F. AI Thinker is the manufacturer. Okay, what does this PDF give us? Shut up. Are you kidding me? So what we're looking at is a data sheet for the ESP12F. Now, it's in a foreign language to me. I can't read this. I suspect this is Chinese. But I would imagine... Okay, there's no... doesn't seem to be a translate option. Is there a different... Okay, so if I click... Okay. So I can click the information tab, the I, and it gives me some good information about this module. I can download that. I'm guessing that's the PDF. Yes, it is. It's the PDF. What would be really nice is if there was a language selection in here. So I really like the fact that you've got access to a PDF document, which has got, you know, the technical specification. Time for Google Lens translation, right? I think what would be better is if there are different languages, that this is something which, you know, you could select the PDF and it would just give you like an EN for English, CN for Chinese, FR for French, you know, and all of these PDFs be, you know, in language friendly to the user. It's on the web, so anyone in the world can use this. So So it would be nice. We've also got Google. Let's be honest about it. Let's have a look. Yeah, it's got 32 megabytes of SPI flash. According to this data sheet. So let's click this and we've got lots of different options, right? That came under the ESP12. So we'll select it and we'll click place. And then we get what we expect, right? We've got this little symbol. That's the right word. We got the symbol of the component. So I placed it, and I can put multiple copies of this if I really want to. But we're gonna just select one and then hit the escape, and we've now got our first component placed. Now I'm gonna move this, so I'm literally left clicking and dragging, and I'm gonna see how intuitive this is. So I'm gonna hit the M for move. Okay, so the cursor is locked to the position of the component. So let us put that in the center of the component and then hit move. Oh, select it first, Steve. And now we can, okay, so you use the right click and drag. We can move around the document. So I'm gonna place this in the upper right corner of my, my schematic. So in a second, what I'm going to do is I'm going to take this schematic off screen and I'm going to move it to another monitor so I can bring this up full screen. But until then, we're going to have a look at what we need. In fact, let's blow this up a little bit bigger. So we have got the ESP12F module. We have a 3.3 volt input. We've got multiple 3.3 volt inputs coming in. We got multiple grounds. We have 2 switches. And we've got 1, 2, 3, 4, 5. We've got 5 resistors. And we have a connector, right? A 4-pin connector. So this is what we're going to simulate or emulate in a second. So let's get this off screen a moment. Let's bring that up here, out of the way. And then I'm going to expand. I'm going to expand. Shrink this down a second. Boop, there we go. Perfect. So we'll expand this full screen and you guys get this in much better definition. Right, so 2, 4, 5 resistors. So let's go ahead and place a resistor. So I'm just going to type resistor, see what we get. Okay, we get a bunch of options here, right? So we can search, we can do sub searches as a particular manufacturer, or we can select a particular footprint. Now I know that I'm going to be using 0805 components, so I'm going to select that. And now I get a list of components that match the criteria that I need for my resistors. So let's place these resistors. I'll just place one for a moment. Yeah, cool. I'm going to hit escape. And this has pulled in an arbitrary value of 365K. Again, I've had limited time playing with this, so I'm learning as I go. I'm figuring this out. So you're seeing this real time. So as a new person coming to this, this is what you would be experiencing. So I'm going to double click the text to see if I can change the value. So how do I change the value? Okay. Okay. So if I click the text, if I click the text, I get this going on, right? It's locked, but if I go to the resistor, it's absolutely fine. Okay. So give me 1 second. I've just got an issue popping up on my screen, which I need to take care of. Technical difficulties. Okay, that should be better. All right, that's how we roll. So we've got a resistor. We're going to change this value to 10K. What would one of my streams be without technical difficulties, right? So we've got one resistor. We need a total of 5. So let's select this. In fact, I'm going to move the text. It's quite a ways away. I'm going to just snug it in here. And we're going to paste. In fact, let's rotate this. So I'm gonna guess if I hit the R key on my keyboard, we're gonna rotate. Are we? We are. Look at that. Excellent. All right, so we're gonna copy that and we're gonna paste it a bunch of times until we get 5 resistors. So I'm gonna grab these and move them out of the way. But what else do I need? I need a ground. Search for ground. Ha! Wait a second. There is these little doodads on the toolbar that we can use to place power. So there's ground. We know we need a couple of those. And then we got VCC. One of the things I need to get drilled in is the super proper matching of any parts I have on hand versus what's out there, meaning I have a breadboard of things I have used. So the thing is, there's a couple of ways of going about that. So if you've got a list, let me keep that on screen so as I'm answering that question, people can reference the question. So if you've got a list of components that you're using and you've got them documented, you can actually search in here for those components, especially if you're doing through hole. The challenge is if you're using a breadboard like this one, which is a solderless breadboard. If you're using a solderless breadboard, you've got things which are through hole components, but the end result may actually be a lot of surface mount components instead, right? So you need to make sure that you've got the parameters of the component that you're using so you can find surface mount versions of them. But if you're doing through hole and you already got the spec of those components, you can search PCBX's library of components to make sure that you've got them. Now, there's a couple of ways, there's a couple of things to think about here. When is it important to have the exact component? It's important when your board manufacturer is assembling the board entirely so that you have a completed board turn up at your door. That's when it's important to have the proper, the exact components. You can be a bit fast and loose if you have the components on hand that you're going to assemble it, providing that you have the correct footprint, so the size and shape of the pads matches the component you're using, and the pad numbering matches what you're going to be using. Then as long as you select the correct footprint, that is the most important part. So it all depends. If the board manufacturer is doing it end-to-end, making it for you, you have to have the correct components. If you're doing the manufacturing and putting it together and soldering, then it's important you have the correct footprints. So that's what you've got to, that's the things that you need to take into consideration. Right, okay. Thank you for that question, CE Waffles. And if there are any questions as we go along, please feel free to ask away. All right, so we got VCC. So what are we going to do here? Let us start arranging the components the way we want them. So we have R1 and R2. I just feel like I'm in an episode of Star Wars right now. Right? And we have R3. Let's have R3 over here. R4 and R5. They'll just go doop like that. In fact, since these are around this side, let's rotate them because why not? R5 can go by here, and we're just nudging things kind of roughly where they're going to be needed to be. We know the next component we need is a switch or a button. So I know EDA software likes to call these push buttons. So let's search for push. Okay, SW for switch underscore push. Okay, we don't have that. Button. Okay. What do we got? So we've got like 39 pages of components. Oh my God. Right. Okay. What can we use? What can we use? Switch, maybe? Okay, so what I've noticed is there is a key down here, and one green has a symbol and a footprint, and there is an amber for symbol and footprint. So there's obviously a difference between these two. So let's just go to 50 components a page. What do we got in here? I need to find something which... represents the buttons, the surface mount buttons that I'm going to be using. And more often than not, this is where the time is going to be spent, right? Finding the right components. Or the right footprint, for that matter. Let me grab a set of digital calipers and a button, and we'll figure out what it is we need, right? So digital calipers. Let's find me a button. It's the trouble with being a maker. You have boxes of stuff everywhere, and storage Well, don't even get me started on keeping a well-maintained storage system. Oh. Is there such a thing as a perfect storage system? I don't know. It's always a work in progress with me. Okay. I need. We're in debug mode right now. How can I keep moving forward? I can keep moving forward by, well, we're going to use you had issues finding the BC547 BJT transistor. Your own storage system only works with you, for you, right? I got you. I know. Right. I'm just looking. I had a button. I actually did have a button ready for this, but it's gone AWOL. So what I'm going to do instead, I am going to use my stream controller as an example, because these are the buttons that I've got. So I did pick up my digital calipers, didn't I? Yes, I did. There they are. All right, here we go. So we've got something which is in and around the 7 millimeters by, I'm being careful not to say mil, by about 3.5, 4 millimeters, 7. So I think my search is insufficient to find said components, right? So we need to find it. So maybe we look down here in this section to see whether or not we can find something which is appropriate. So what do we got? Recent. So capacitors, inductor coils, diodes, resistors, transistors, linear ICs, connectors, switches. Okay, cool. Tactile switches. I guess it's a tactile switch. Button. Where's the button? I know, right? So we got an 0603 metric. That's not what I've got. Uh, 7 by 4.4. Looking promising. Okay, so this is a horizontal, right? I need a vertical. So we're very close. 7 by 4. What else have we got? Oh, actually, was there anything else in that list, or was it just one? I did a schoolboy error and didn't check. Okay, so there was only just one. Okay. Let's see what else we got. I keep selecting the same one. Oh my word. What's wrong with me? I am broken. That's roughly square. That's not really right. So we want an SMD. Single pole, single throw. Okay, we're getting closer. Let's see what we've got in here. Like the library is pretty extensive. I'm quite I'm quite impressed by what is in the library. This is really, really cool. Although choice can be a bit of a pain, right? We got 58 pages. Oh my word. If only I knew what I had, that would be useful, right? Because then I could search for like the component, but I'm actually looking for something that I'm unsure of. Okay, we're in zone. We're in the zone. What do we got here? Now we are going to be placing an order at the end of this, so I need to... There you are. There you are. That's the chappy. Okay, we got a 12 volts, 60 current rating. Okay, I think this is going to be the one. So, okay, so we'll rotate it and we'll plop one by there and we'll plop one by not a fan of the footprint, not a fan of the symbol, but at the end of the day, what does it matter if it works, right? So, okay, so now we have to start connecting things. Oh, we forgot a connector. So let's put in a connector. Let's try this library from the side here. Connectors, terminal. Oh, headers and wire housings. It's probably more what we want. It's a 2.54 pitch. Okay. Okay, gotta find the connector. It's a pin header. Okay, would help if I spelled header correctly. 2.54. Okay, and we want... Okay, 1 by 4. What do I get if I put 1 by 4? 2.54. Okay, we don't have a symbol or footprint. All right, let's try terminals. Terminal. 2.54 is what I'm after. Yeah, I don't think that's what I want. Okay, so now I'm falling foul as a newbie. I'm falling foul of this search feature. Molex. Okay, what about DuPont? Huh. So I need something, essentially, it's a 2.54. It's asking me for wire gauge, so I think I'm in the wrong place, right? So let's go all. Uh, 1/4. $2.54, and all I get is these connector type header, female. That's the thing. That's what I want. Okay. What if I could I put data? Okay, I can't select that. Oh, that's a challenge. All right, we'll come back to this. We'll have a think about it. If anyone's got any suggestions, feel free to post into chat, and we'll see whether or not we can figure out how we can get that to work out for us. Right, so I'm just aligning up the first VCC, and I'm going to start wiring. So I choose the wire tool, and we select that, and we start connecting the 2 points. And now you'll notice that each component has got like a little circle. Right, it's got a little circle on the bottom of it. Now, when we make an electrical connection with it, you'll notice those circles disappear. So that's how you know that you've made a successful connection. Alrighty, so we know we've got VCC coming into R3. So let's use that align tool, shall we? Let's select these two components. If I right click, have I got an align? Okay, we don't have it here. But if I go to view, where is it? Place. Where's the align? Where did it? Edit, align. There we go. And we want them to be centered. I like that. I like that a lot. So now I can just go and connect that. If I do that with this switch as well, and also this resistor down the bottom, like that. Ooh, I've selected the label of the other one. And I say edit, align. And this is purely for aesthetics, right? I don't have to do this to make it work. It just looks nicer. Okay, so I'm just checking my diagram. GPIO 15 goes to R5. So let's just wire that to there, like that. And then we've got GPIO 0. It goes... Do you know what? That resistor is lower than it needs to be. So can I grab it and move it? I can, but it's now kind of made it a bit weird. So I need to delete the lines. And that's common in EDA software, to be honest with you. Now I've moved things around. What I did notice when I tried to move it, you can't like just press the up arrow and then just move it in the up direction. Because that would have been nice, but not the end of the world. All right, so select it. In fact, let's bring you in line with that. Trying to make this look nice. Half the time, it can be making your circuit look nice as opposed to functional, right? So align vertical. And this is where I should learn a shortcut. Take my own medicine, right? I'm going to connect these all the way down to the final resistor. Like that. Now GPIO 18 comes over and boop. Now I haven't made a connection. How do I know? Because there's no circle. So I did it wrong. So let's select it. Click on the line. Double click, and then we've got a connection. Perfect, perfect, perfect. Alrighty. So let's align these components. Okay, and let's use this align tool to align them horizontally, like so. Perfect. All right. And we'll connect these up. Move this over to the side. We need to hustle a little bit, so we in line? Let's find out. Oh, we're just off. Isn't that a pain? All right, so let's click this line here. Select it. There we go. Happy days. All right, we're almost there, right? So let's grab these two resistors. Hit escape to cancel out everything. Yeah, we can keep them reasonably close together. That's fine. Edit, align, and we'll align their centers. And now we go move. We're going to bring them above. And we're going to put this VCC. Whoop. Put this VCC. Move. Approximately in the middle. And now I'm going to draw a line from here to there, and then from there to there. Oh, let's zoom in. Let's make it a little bit easier on myself, right? There we go. Now we're cooking. Okay, so R1, we're going to push through the switch. Just going to rotate it so that the fonts are all on the other side. I don't have to. I could have just moved it. It doesn't really matter at this stage. And we're going to place a wire from there to there. Okay, and then we've got this final ground. We're going to put roughly down here, and I'm sure I've not got that aligned right. So let's grab these components like so. I'm going to go align. This could break things, but it looks okay. All right. Have we got any suggestions on how we can fix this this connector issue? Because we do need to fix that, right? So we're going to send... Yeah, we're going to send the reset to the switch. So when we press the reset, it just grounds it and the microcontroller will restart. We also then have to bring this to the enable pin so that that will function. So this is good, right? I like. So Now we got to place that connector and get that connector fixed. So how are we going to fix that problem? Because I couldn't find the component in the list. Yeah, I could be being dumb. Okay, just call it header. Okay, what do we got? Female. Ah. 1x3, 2.54 female. Okay, we're in the right place. 2.54. So let's get rid of all of the components that we don't need and just isolate to 2.54. Now, where did that go? E equals 2.54. Okay, that search is not as intuitive as it could be. All right, let's change this to 50 components per page, and hopefully we can find the connector that we need. And this is going to be the header pins that we're going to use to power and program the device. Okay, that's a 2-pin. PH3 doesn't have a footprint by the look of it. We want a 1x4, right? That's what we're after. That's a 24-pin, but doesn't have a footprint. It would be nice to filter out ones that don't have the footprint. That would be a nice option to have. Okay. Gonna look for something that is roughly what we want and maybe search for that manufacturer or for that part. Okay, so there's no footprints in here, so let's go to the next page. This is going to take a while, I think. So this is something I would definitely say that needs to be looked at as improving. There's 127 pages of this, so... Okay, what do we got? We got some footprints here. None of which that I need. This is a little frustrating. How can I fix this? I guess this is where too much choice is a bad thing. Okay, we got 9. We're down to 9 pages when we go 2.54. So let's see what we got, right? I'm hoping we're going to come across a page with all of the components that we need very shortly. Otherwise, we might need to skip ahead. which means I won't be able to place the order. If I don't have those header pins, that's going to be problematic, right? So all I'm doing is moving from page to page, scanning where we've got symbol and footprints. And there's a lot of entries in here. So there's a lot of components that the manufacturer's got access to, which don't have footprints and oh, here we go. What do we got? Okay, so we're now getting into some sort of, these are Molex connectors. Okay, there's 14. Is that 14? Is that 14 or 15 pins? No, it's 2-pin. Is that a 3-pin? I'm trying to work out the... Yes, right. So that's a 3-pin. I need a 4-pin. I'm looking for... So this is a 5-pin, I'm guessing? No, it's more than that. TW04. Right, remember, it's just the footprint I'm interested in. So, Yahtzee, winner, winner, chicken dinner. Found it. Okay, so let's place the component. Oh. Okay, let's rotate this round. So these are pointing upwards. And can we mirror it? Can we mirror the component? I like pin number 1 over on the opposing side. So the mirror, reflection on X. There we go. Excellent. It's just me, right? I've just been weird like that. Let's move the name of it over here. All right. So what do I need? I need power. I need ground. I need TX and I need RX. So the power and ground is relatively straightforward, right? So let's get the power and ground. Ricey waffles? Yeah. I mean, it's really good that they have so much choice. But I guess as a newbie, too much choice can be a problem. So let's place the ground here. And I'm going to place the components before I'm going to wire them, right? Yes. Yes, I do need a ground. Thank you. All right. So now we need to put some labels in. So let's see if we can... There we go, global label. And I'm going to call this one TX. I'm going to put that by there. And I'm going to need another one called RX. Now, I like global labels because they work everywhere, but reality is you should probably like localize things as much as possible. But, you know, I'm not a professional. I'm a hobbyist. So take that as take that with a grain of salt, right? So let's move these so they're roughly in line with their corresponding pins. Now the question is are we going to get this done in the time that we have available to us? I'd like to think we do. So let's align and horizontal. No, that's not going to work for us. Let's align bottom. Can we align bottom? Align top, align bottom. Boop. Done. Okay, so now we can go ahead and route the wires from one area to the next. Okay, that ain't perfect. That's slightly crooked. Ah, that's going to irritate me. That's going to, like, zap my OCD brain. I think that's either a grid spacing issue or that is a component placement. I'm going to say it's my grid. Okay, so I'm not going to try and fix that right now because we've taken enough time as it is to do what we need. Right, so let's save this. If it doesn't automatically save, let's just make sure we've saved it. So that's the core. We need to move on to, let's have a look, our control. So we need a channel. Oh, I'll tell you what we need as well. We need to grab the TX and RX pins. You need to copy them and paste them. And we need to plunk them down over here and connect them so that we can program our board. So let's see. TX goes to pin. It goes to GPIO 1. There's GPIO 1 on here. Oh, it's over the other side. Duh. It's over. Come over here. All right. Okay. Yeah, these are slightly out of line. I don't know if that's my eyeballs or... Yeah, there's a slight spacing going on in terms of the footprint. It's just triggering me a little bit, but, you know, I can live with it as long as it works. Thanks, CU Waffles. I appreciate that comment. I resemble that remark. Right, so the next thing we need is a button. So we've got one here, which we're going to just recycle out of the schematic. And then we need... We need a 2-pin connector. All right. So I'm going to search. I'm going to search for a new component. I'm going to learn a lesson here. I'm going to search for TSW-10 and then see what I get back. Right. Can I move this? No. Right. So TSW-10 return. What do I get? What do I get? Come on. O2. I'm kind of guessing what this needs to be. 2.54 pin header, perfect place. Okay, place that there. I'm going to mirror it. Reflection on the x-axis. Oh, nuts. Okay. Edit. Reflection on the x-axis. Oh, have I just undone it? Am I being a doofus here? I think I am. There we go. The text not moving kind of threw me. Alrighty. We'll align the centers. And what I'm doing here is I am creating a button. So we got local control of the channel and the actual output that's going to drive something. Okay. So we shall create a global label and we'll call this button A. And then we're going to pull this down to ground. And then we need a ground. Copy paste that from this diagram. And we need another label called channel A. So let's call this chan A. Okay, we'll rotate that. And we will drop this down here. And then we just need to connect the wires. So this is going to be the output of the controller. And this will be connected to a socket. This will be a wire soldered to the board. There's any number of things, right? This could be. And we'll just connect these wires here. Okay, let's hit the save button. Okay, so now I'm going to select these two labels. And we're going to bring them up to the microcontroller and we're going to place them. Okay, so my channel A goes into GPIO. No, it doesn't. No, it doesn't. Channel A does not. That comes off a MOSFET later on. That's fine. So button A, where do you go? Let's go GPIO 2. Okay, and then we're going to select that and draw a wire. So my button is now coming in, and I need an output now. GPIO 12 we're going to have as MOSFET A. Because we're going to use a MOSFET to drive the output. So a MOSFET is a type of transistor that can handle quite a lot of current. You still can't use it with mains voltages, but you can use it with low voltage and high current. So we'll call this MFET A, GPIO 12. And now we can just kind of click on here. All right. So that's this portion of the circuit complete. So now I need to move on to the next bit. The next bit is, so we got that bit done as well. So we got the buttons and the outputs. So next up, we got the MOSFETs. Right, so let's find a MOSFET. So this is an N-channel MOSFET. Let's just search for MOSFET and see how the naming convention works. Let's see if we can. Let's see if we can. It's going to be a. I'm looking. No, it's not that. Okay, I've actually got a component here, so let me just switch. I'm going to try and shortcut this process. Let me just find the package that I used for this MOSFET. I'm just going to go and check my orders. See, this is where, as a newbie, we fall down, right? As a professional, you'd have all the components you got listed, and you could probably search this database really quickly. So for somebody who's more proficient with these components, it's going to be a nice experience of having such a diverse library of things. As a newbie, then it's a little bit more challenging. But all right, so this is an N-channel MOSFET. What do we got? Have we got package dimension? Oh, manufacturer's reference. Here we go. Can I use that? Can I use this manufacturer's reference to find in the database? That would be cool. Let's try this. So if I type in that, is it there? Oh, boo. Okay. Okay. That's a shame. Let me see if I can find a reference for this component. Let's find a data sheet for it. Okay, I'm searching for N-channel MOSFET. All right, so let's bring this on screen and you guys can follow along. Okay, so let's go to here. Right, so we got a Pi Hut MOSFET, 60 amp. This is a 60 amp, right? What do we got? Have we got a package information? We got specifications here. Pi Hut are usually pretty good. Few more. Right, it's a TO 220 package, right? So let's search for a MOSFET with that package. Well, that's silly, right? I search MOSFET. Do I have a package footprint? Awesome, awesome. So we're narrowing down the search. Okay. Why did that come back like that? I don't want that. Although, that's ITO. That might be something I can use. I'm not sure. Let's check. Let's try and get the right footprint. Here we go. Now we're cooking. Okay, now the question is this the correct type of MOSFET? Doesn't look like it is. These are all N channels. Huh. I need to check the specs of the MOSFET I'm using. Have I... Ooh, maybe I've got a P channel MOSFET. See? I iterate. I iterate through my problems. And I'm a good example of perseverance. These are N-channel MOSFETs, so okay, got to trust the process. The diagram I'm looking at looks like I might have used the wrong ones. Oops. Anywho, the pinout should be right, but yikes! I'm noticing some errors in previous works, so that might be where I'm going wrong, right? But anyway, we'll try. We'll trust the process. We're gonna find out if this works. Right, so let's rotate our component. All right, let's place it here. Alrighty. So we also need an LED. And we want an 0805 footprint. That'll do nicely. Grab that component, replace that. Like so. And that's going to be in parallel. So when this is in operation, this will work. Yeah, I think I've used the wrong MOSFET in my other example. So I may need to modify. We will see. All right. Yeah, no worries. Thanks for that. Appreciate it. Okay, so this is going to be pretty easy, right? So we've got, I'm going to draw a wire between these two components, right? Like that. And then we're going to draw a wire in between the gate here. And then we got a line that comes off down underneath, right? Which we're going to, in fact, no, we'll place a label first, right? So what do we call it? Let's grab, we'll use, we'll copy that. And then we're going to place it down here. So we've got an output coming to this here. And then we've got channel A, which is the output to the device that we want to use. I'm going to copy that. And we're going to rotate it. And we're going to put it here. Okay. Let's start to speed run this a little bit, because we still got quite a bit of work to do. Okay. One final thing that we got to do is get power into this unit. So let's have a look at my power circuit. So we want a 2-pin connector, TSW102, I reckon we're going to need. So let's try that. TSW 102. Let's search for that. Ah, no, not a MOSFET. TSW. There it is. Search. Oh, wait. Ah, my mouse is not mousing. TSW. TSW. Right. Okay, that's searching for it. There it is. Okay, place. And let's just pop that over here. Now this is going to be very interesting to see whether or not we can get the components that I need now, right? So I need a voltage regulator. And the part number for this is SPX3819 M5 L 3-3. And there it is. Voltage regulator. I'm liking that. All right, we're gonna just pop that by here. And we need a capacitor. It's a tantalum. I can never spell it right. Okay. Okay, so that's the one. That's the chappy. Okay. We're on the final stretch here, I think, of the schematic. Let's get a couple of grounds in here. And this needs to be mirrored because it's facing the wrong way. All right. Okay, and we need another ground just here. And we can now start to wire everything up. So we need a ground wired into here. We need a ground wired into here. And it's always important to wire your grounds in because if you don't, things don't work. If you know, you know. All right. So pin 5 is our voltage line out. That becomes 3.3 volts. So let's get our VCC. We'll call VCC our 3.3 volt line. Now we're going to pop it by there. Right, okay, that's cool. And now our voltage in goes to pin 1. We also loop in our enable. Without that, the voltage regulator goes to sleep. Okay, and now we could probably leave it at that, but there is a 12 volt feed coming in here. We'll see whether things complain. So let's let us go to our tools and update the PCB. And here are all of the components that we're going to be using for our PCB, right? So one of the things I want to do is I just want to get a rough idea of where my components are going to sit. So if I select, we've gone immediately now into the PCB section over here. Okay, we want our, what do we say? I got to find my components right. J3 is our power input. So J3 is our power input. So I'll put that down here a minute. I'm going to go back. J1 is our programmer. Move. I'm going to pop that just there. This is our MOSFET for triggering. I believe J2 is our output. So let's... Tell you what, can I group these? That would be cool if I could. Okay, that's a shame. It doesn't look like I can group them. That's fine. Okay, so we've got our voltage regulator. Let's grab these. I want to keep this board narrow. I'm going to point VCC vertically from our voltage regulator. And I'll tell you what I'm going to do. I'm going to rotate that just so that my wires are not kind of all tangled up. Okay, my tantalum capacitor, let's bring him over here. And all I'm doing is I'm just nudging the components around the board until I get this laid out. So we know R1 and R2 are quite close to each other. But they need to be on the other side of this chip. So we'll just check them over here because I want them close to where they need to be. Pop that down here. I'm guessing these are going to need to come down here. Yeah. So I'm just nudging them closer to where they've got to live. Okay, so button 1 was reset, button 2 is program. Usually the program button is on the right and the reset button is on the left on like the Wemos D1 Mini. So we'll try and keep to that sort of convention. I'm going to add an additional button, which is going to be down here on the side. And I'm also going to bring the LED in here. Now, this looks like a big mess, right? You see all these little gray wires, or these little gray lines that are like all over the place. And the whole purpose of these wires is to show where the pads of the component actually connect together. They're called air wires, and if you've got these, it means that you're missing copper traces. So we don't have a circuit yet, right? We know we've got these components that need to connect together, and it's like a big jumbled mess at the moment. But in a moment, we're going to just hone this in and just make sure we've got it as we need it. I'm just going to check something before I go too deep into here. I've just realized I've missed something. I thought I had. I've missed the ground. That would have been embarrassing. That needs to be there. Now to update the board, we've got to go tools, update PCB. Yeah, that would have been embarrassing. I noticed that there was no ground on this LED, which that's not a good sign. Right, let's rotate this LED. And all this is a signal that the device is actually active. I'm going to edit. I'm going to align these now. Oh, I've chosen the wrong align option. We want align. What does baffled mean? Baffled means me. Right. Edit. Align. Where are you? Can't see the wood for the trees. Align horizontal centers. There we go. That's what we want. I can't seem to select the text. Can I select the text here? I can. Okay, so that's going to be a problem. Let's grab that LED text. Move. Let's put it. Okay, I'm having fun with my grid. Okay, I've just changed the scale of my grid, and hopefully, oh, it's not quite. I need to go a bit finer. Okay. There we go. I can now bump it back up to 0.254. All right, we should be moving along pretty quickly now. So that needs to be connected to VCC. And it needs to be connected. This resistor needs to be connected to this switch. I'm going to pop that by there. Let's see where this one needs to go. These two need to be close together, possibly. Let's rotate it, and you can see the lines untangle themselves. That's something I like to do, is look at the air wires and see where my component is. If the lines cross, it means you're going to have fun trying to route those wires to the components. That's not ideal. So let's grab this component. Let's see where this needs to be. If I pop it by here, where do the air wires go? This also seems to be connected to... Let's grab these two components. Let's move them. And we're starting to stack, and we're starting to get some sort of order. I'm going to nudge these in close because I want this to be a relatively small package. And we may still yet move things around. Let's align these on their centers. Edit. I like the align tool because if you're having issues with your grid, in terms of the pitch of the grid, then this can really pull you out of a problem. I think what I'm going to do for a moment, I'm going to grab the components just here. I'm going to grab this component here. I'm going to move this out of the way. And I'm going to move this button and this LED out of the way. Oh, come on. Select, and control, select, move. Yeah, there we go. Right, I'm going to bring these buttons together. These buttons are only going to be used for programming purposes and like just general resets. So I'm not overly worried about them. Let's move them a little closer. Right, this, and let's align them centered. So all we're doing here, right, is we're just pushing blocks around a screen in order to get them to look aesthetically pleasing. Now we're going to be making a double-sided board, so I can kind of nudge this up right close to the bottom of the ESP12 module. Now, if I could group these items, I could then sort of align them, the grouped items with other components, and it gives you the ability to kind of nudge them into a really nice sort of, a really nice aesthetic. So, but it is what it is. Let's rotate these. Just going to pull that out so I can select the text, and I'm just arranging the text so it's out of the way. And I'm starting to speed run this a little bit. Okay, so we got a keep out zone that we know we got to adhere to. So I'm gonna bring that down, and I'm gonna bring the programmer. Where's my programming pins? My programming pins are actually on the other side, so I'm gonna swap sides. I'm gonna bring it down to here. And then I'm going to now we're building the output. Awesome. Awesome, awesome, awesome. Right, okay, this is making a lot more sense to me now. So I'm going to grab my MOSFET. I'm going to bring my MOSFET, and I'm going to put my MOSFET alongside my switch. In fact, I'm going to rotate it, making sure that my channel is pointing down. And that makes it wiring the output a lot easier to the jumper. So I believe jumper 2 is my output. So I'm going to put that by here, and then I'm going to put this by there on the other side. And I'm just going to bring this text up the top. And now we're just going to align these components. We're almost ready to start running traces. And then I'm going to stack those components there. Okay. So now, here we go. We're going to create a board outline. So let us select the drawing tools. I want this, change this to be, what do we got? Top cover, top paste, silkscreen, courtyard, drawing, eco, bottom mass, outline. That's what I want. And I want to select a rounded corner. Let's have a look. Because one of the things I like is having rounded corners on my circuit boards. Round effect. There we go. Millimeters. I'm going to have a 3mm radius on this. And then I just grab. And I'm drawing on the bottom copper, aren't I? Like a doofus. Let's try that again. Oh no, the color tricked me. Okay, so let's use my select tool. Okay. I want to try and get that centered as I can. I think that's about right. And I've made the board slightly bigger than I need it to be to some extent, because we're now going to place some components, right? We're going to place 2 vias. So let's place root via. Okay, so I'm going to change the hole diameter to 3.2 millimeters. It's a through hole type. No net. And then I'm going to place it by there. I just undid that, didn't I? Place via hole diameter 3. So this is how I'm placing. Okay, it needs to comply with DRC rules. It's complaining at me. Ah, no. I had this problem before, and I thought I'd fixed it, but my brain is not working. 3.2 via diameter, hole diameter 3.2. .2. 2.54. Ah, no! Bugger! I'm completing at a doofus. Right, so let me save this a moment before I break everything. DRC rules, right? Edit. Okay, so let's have a look. Via diameter. Okay, so maximum is 2.54. So I'm going to go. Maximum is 3.2, and the maximum is 3.2. And we'll save. And let's see if I can now put 3.2 in here. Okay, what have I done wrong? This is all on me now, right? .2. Okay, let's see if I can do this. Oh, unplated hole. 3.2. I've really messed it up now, haven't I? I've really messed it up. Ah, what a doofus. Okay, unplated hole. Via diameter. Okay. Can I go in here? I will give that a try. Give me one moment. I think I've made a mistake. I think this is me. Okay, cool. Save and run. Okay, can I choose a 3.2? Ah! The hole needs to comply with the DRC rules. Via diameter needs to comply with DRC rules. So it's complaining, right? No. So I thought unplated hole, I could just type in the details. Right, so tools, design constraints manager, routing. Ah, okay, bin that. Okay, confirm delete. Width 1. Okay. Max width. So if I put in here 3.2 and 3.2 and then save and run. I did this once before. I don't know why. I don't know why I've completely messed this up. It's always when somebody's watching. It is always when somebody is watching that you mess it up. Okay. Let's see if I can. I'm going to save this a moment. And I'm going to come back to my workspace. And I'm going to reload the workspace just in case this is just me being single channel low voltage. Boom. If in doubt, come out and back in. Remember, this is a beta and I'm a newbie. So the chance of issues, well, it's great. All right, root via. Unplated hole. Okay, via diameter is. Have I? This looks like we've got a millimeter to millis sort of conversion issue. Tools, design constraints manager, routing via, right. Preferred is 127. Hey. Oh, I've just added a new one. All right. So if we say we want a 3.2 millimeter hole diameter and 3.2 millimeter. I think that's a big hole. 3.2. It's jumping back to the preferred, right? So what if I go into Design Constraints Manager, routing? What's irritating is I've dealt with this before, right? I've used this before. Preferred 3.2, 3.2. Okay, minimum. Ah, right. Okay, minimum 1. Preferred 3.2, 3.2. And we'll leave the maximums alone, right? Save and run. Okay, so it's still not liking it, right? How did I fix this before? Right? Yeah, you're not wrong. You're not wrong. I think this is this is a bit of a challenge, right? Now, I did have this problem before, and I managed to resolve it. So what I'm going to do is I'm just going to quickly save this, and I'm going to jump back here. I'm just going to quickly create a new design. I just want to experiment here a moment without doing anything bad to the other circuit that we've worked on. So let us update PCB, right? Let's go to the PCB, and I'm going to draw an outline. We're going to put this on here. Okay, and then we're going to, what did I do? Yeah. Oh, I'm zoomed way in. Why am I zoomed way in? Okay, so there's my board, right? And we want to route a via. We're going to unplated hole. This is going to be 3.2 millimeters. Via diameter is 3.2. Oh, 3.2. What have I broken? I've broken something. Okay, minimum diameter 1. Why is the minimum diameter like huge? So let's go 0.25. A reset button would be really nice right about now. 0.25. Okay, let's just see what on earth have I done? Oh my word. Okay, so 3.2. Can I put that in here now? 3.2. I think I'm getting there. I think I'm getting there. Okay, let's try that once again. I think I know what I've done. So via diameter 3.2, and we're going to place it there. How big? My word, how big is this? What have I done? It's getting late for me, so I'm making all sorts of silly mistakes. Okay, round rectangle, radius 2 meters. I'm going to change my grid size. Where's my grid? I'm going to change my grid. Right, these are in mils. So let's change that to millimeters. And we're going to go 1.27. Perfect. Right, okay. Now I can route my vias. We're going to say an unplated hole. Now that's more like it. There we go. So if I look at the 3D view of this now, I should have a board with a hole in it. Right. I do. Yay! I've got a board with a hole. Now let's see if we can take this back to the other file. All right. So let's go to the low. This is all on me. Right, okay. So let's go to our PCB. Let's go to our... Let's see if we can correct our mistake, right? Let's go to our Design Constraints Manager. Let's go to routing via... So there's the first one. So that's fine. Let's bin that off. Confirm deletion. Okay, and I'm going to take a quick screenshot of this so I can at least come back to it if I need to, right? So I've just taken a screenshot of that. Let's minimize that. That's going to bug me otherwise. We're going to delete this. Last menu item, can't delete it. All right, create a new one and then delete that. All right. Okay. So the via diameter minimum, we're going to make the minimum 0.762. The preferred 1.27. Maximum, we're going to say is 100. Hole size 0.4064. I'm reading off my screenshot. 0.7112. Maximum 49. Save and run. Okay, so we now have hopefully the ability to place some vias which are unplated through holes. We want the hole diameter to be 3.2 so we can get an M3 screw through it. And it's going to a maximum of 2.54. So there's something buggy about this now. I've broken it. Dang it. All right. I'm not quite sure what I've done to damage it. But I've broken it. Let's go preferred diameter of 5. Save and run. So we're going to go 3.2. We're going to go under the... See, it just changes it back. 2.2. Why are you doing that? I'm stumped, being honest. Can I trick it? Can I trick it? Okay. Routing via. Let's go 3.2. I'm gonna go 3.2. Save and run. I'm face palming so hard right now, right? Because I had this working before. So I'm gonna place one there. I'm going to place one there. I'm going to place one there. And I'm going to place one there. Okay, cool. Okay. So I'm going to select these two and we're going to align them centrally so that they're in line. Boop, like that. I'm going to do the same with these two. View, edit, align, center. Cool. And now I'm going to, did I align that? I don't know if I did. It looks a bit wonky, so I'm going to do it again because you know me, I'm likely to make mistakes. There you go. It didn't align. Right. So I'm going to select these two now, and I'm going to align them. Like so, and then I'm going to align them like so. I am really despite the challenges, I am actually really enjoying this. Okay, so if I do a 3D view now, we'll see my circuit board, hopefully with all of my footprints, all of the bits and pieces that I need for a single channel device. I'm really liking that. Okay, I could probably make it a little bit smaller, but given the time, we're just going to push on. Okay, so let's look at running a ground plane. So one thing I do like to do is to have a ground plane that covers the entire board. And then when I draw my traces, what happens is it cuts out the traces in there, but my grounds are still connected. That's the theory. You can create islands that if you rely on them, then there's a problem. But what we do, we create a copper zone. And we're going to choose a top copper zone. And I'm going to draw a box around my board, right? And this represents a copper flood, if you like. So now all I need to do is concentrate on wiring connections from these components, right? So we're going to route tracks and we're going to go from here to there. And we're just going to literally draw lines. Now you might think, wait a second, Steve, you've got a problem because your ground line is now like all over these traces. But what you do is you select the ground plane. Oh. So if I select this copper ground plane and right click it, it's actually set to no net. So let's select this to ground. Right. So let me zoom out, right click, and if I report all copper, it now creates this little cutout. So these are all isolated, which is what we want. Okay, so now we can run a VCC line. Now these things don't take any sort of like current, so they don't have to be like super wide traces. Which is good. Okay. And we just need to make sure at the end of all of this that we right click and we select our pour the selected copper, and then we isolate the traces that we just created. So that's pretty much what we got to do now. Rinse and repeat. Rinse and repeat. So let's get on with routing these wires. Now, what would really be nice is some sort of auto router. Now, as I mentioned at the beginning of the stream, this tool is in beta. So at the moment, the auto router function does not function, but it's something that is being worked on. Okay. So I'm going to see if I can do this without any vias, because we know we've had some problems with vias tonight. So let's not play with them too much. The via gods will be upset with me. Right, so I'm going to see what I can do here in terms of routing traces. Let's see if I can be a bit sneaky. Can I route? Okay, I need to change my grid. I need to have a finer grid. So let's go down to 0.127. Why is that not? Oh, there we go. I'm going to try and sneak a trace through here. Okay, let's just do a copper fill. Splish splash, done. Okay, we now got to sneak. We gotta get VCC. We may need some vias here. We may need some vias. Okay, let's route. Let's route this one first. And this is where an auto router would come in really handy. Oh, that doesn't look good. Because it would take a lot of the heavy lifting out of wiring the traces. Now I'm able to sneak these wires in here because they are low voltage, right? They're signal wires and they don't have to be particularly heavyweight copper in order to do their job. Not yet, anyway. This is probably not going to be my finest hour in terms of manually routing these wires. But we will do the best we can. And I think we've hit a point where we need some vias. Okay. All right. So here we go. Let's now concentrate. What do we got left to do? We've got all those routed at the top. We've got VCC on our programmer. Exactly, Gary. Exactly. They take you on to the other side. Okay, so I think I might have just spotted a way to get myself through this. I'm going to grab a trace and see if I can sneak it. Will the DRC allow me through? It will, by the look of it. Oh, we got a clearance error. No! Okay. I only fixed that. Surprised we didn't get a clearance error with this one then. All right, it's a through hole, right? It's a through hole component, so I can actually route this on the back side. That's not what I wanted to do. Undo is your friend. Okay, so let's run on the bottom copper. All right, we'll run from this. And we can run over here, right, to this point. And then we can route a via. Now, have I broken the vias sufficiently? Yeah, that doesn't look right. That via definitely looks a bit ill. So what I'm going to do, I'm going to delete that. I'm going to come back into my design rules. And I'm going to set the vias back to their defaults. So let me just grab the default settings, which I saved, thankfully. 1.27. 3. That wasn't 3.1. It's 3.199. But that was me playing, right? And then 07112 and 3.199. Now, if there's an option to save that, that would be really cool. Now, I'm just wondering whether or not it's going to break my mounting holes. Looks like it might. No, I don't know. Is that broken my mounting holes? No. No, it hasn't broke my mounting holes. Cool. Good. All right. So let us close this window. The path of a maker is never smooth. All right, now we can say we're going to place a via. Uh, 1.27, wasn't it? 1.27. Damn it, it needs to comply with the rules. Well, I thought I was. I thought I was complying with the rules. Okay. So we've got one via in there, VCC. And we're kind of penned in, so we'll do, what we'll do is we will go back to routing tracks. Okay, we'll place a via. Like so. And now we're going to route the tracks on the bottom copper. From there to there. And now we can route from here to there. Now I'm going to increase the copper size here. Let's go 0.4. Ah. Okay, that's the thing with the fill. The fill is on the top until you pour it. Okay, so let's just delete that a second. I'm gonna put a trace in here which is 0.4 because it's gonna handle a little bit more current. Line width 0.4. Like so. This one's going to handle quite a bit of current, so I'm going to actually beef this one up pretty big. All right, I think I can edit this. Give me 1 second. Let's see if I can edit this. Right click. Core this layer. Okay, so we're going to select this wire and we're going to go 1. Okay, Control Z. Let's choose this. Can I select this wire? Ah. Okay, 1 millimeter. This is going to be like a real big chunky boy. Like so. And I think I've made an error here. Yeah, I think I have, but we shall see. We shall see. We'll finish routing these wires. All right, so this MOSFET signal, then we're going to have to route this. We don't want it that chunky. We don't want it that chunky. I know what I've done wrong. I know exactly what I've done wrong. I'm going to have to update the board. I've just twigged what I'd done. Stupid, stupid. But anyway, we can fix it. We can fix it. The path of the maker is plated with... Ah, that's funny. That's quite funny. I like that. Okay, I gotta stop trying to do that. Okay, I'm gonna copy this trace width. I gotta go back to a signal wire. Okay, so like I say, this is not my finest hour in terms of routing, because I'm doing this all manual, right? So I'm just gonna bring that to here, and I'm going to change this. Yikes. Perhaps I should do the fill afterwards, right? Copper zone. I want to flood. I want to pour. Okay, so let's get rid of this trace a moment. We're going to write... There we go. There we go. There we go. Now we're cooking with gas. Okay. Going to pop that there. We're going to put a via down. Like so. We're going to now route my tracks on the bottom, because we're free to route wherever we need to, and we can just come straight into here like so. We can now jump back to the top track. And we can go from here into there. And we've only now got this island, this VCC island to fix. So if we route from here to there, we're done, right? Now I gotta fix my mistake. So we'll save that. We'll come back to the schematic. Okay, so channel A is a ground, right? Channel A is a ground. So I do need to place a label here. So let's place a label and call this 12 volts. And connect that in like so. I'm going to copy this label, and I'm going to bring it down to my output. We're going to delete the ground. I'm going to move this into position. We're going to save, because the MOSFET switches the ground. The MOSFET switches the ground. Duh. Right. And now we update the PCB, and let's see what that's done. Okay, so now we need a pretty chunky trace going between these two pads. Not on... I could probably put it on the bottom copper, actually. But I want to try and keep the vias to a minimum, so we'll put it on the top. Okay, so now let's select, right-click, and pour this layer. Okay, if I do a DRC check and this comes back with no errors, I'll be amazed. Let's see what we got and whether or not we can live with it. Okay, unrooted. We got unrooted. Ah, okay. My enable pin is not rooted. Well, I'm glad we caught that. Because that could have been a royal pain in the bum. We would have never figured that out. I would have had to have had an air wire. Gosh, me put air wires in a circuit? Who'd have thunk it? Okay, pour this layer. Okay, let's run a DRC again. So design rules check. Let's check in to see whether or not there's any problems with this circuit based upon our drawings. Let's have a look. Clearance constraint. Where is it? Ah, okay. Well, it allowed us to route that. That's interesting. I wouldn't have anticipated that allowing me to... Okay, we'll flip the board. Okay, we lost our copper now. Okay, that surprised me that it let me route that way. So let's just put this in separately. I'm penned in here. So let's come the other way, shall we? Okay, it's selecting that component. So that's irritating. Okay, so can I... So it's selecting. Oh, here we go. Got it. Okay, cool. I needed to select the top copper layer. That was me again being a doofus. Correct. That's the idea. I mean, this is a low voltage system, so it can pull 3 amps. And should be fine. Okay, so now we can route a trace on the bottom. So how I managed to get those streams to cross like I did is beyond me, right? Like I say, this is a beta tool, so I mean, it's not necessarily going to be perfect. But as I said at the beginning of the stream, nothing ever is. All right, we seem to have lost our copper fill, so let's put our copper fill back in. We want top copper. No. Stop that, Stephen. Okay. I need a copper zone. Okay, we want to choose ground. And then we want to just outline the board. And it doesn't, you know, as long as it encompasses the board, it can be pretty much any shape. Like that. Select it. This is going to really trip some people out. We pour the layer. Bloop. There we go. Alrighty then. So let's do our DRC again. Let's see what else we've got problems with. Okay. Error type, 16 errors. Via constraints, 8. Hole size constraints, 4. Annular ring constraint, 4. And this is all to do with those vias. I think we can probably work that out though. That's fine. That's the via setup. So the holes should be fine. Annular ring constraints. What do we got? Again, this is all on these holes. So I'm not overly worried about those right now. So that's the biggest thing, right? About the holes. It would be nice if there was a footprint that you could just drop in as a particular mounting hole. And that would deal with all of these sort of constraint problems. But for now, I'm not overly worried about that. None of the vias that was complaining. So I think we're good to go. All right, so there's our board. Right, we probably need to add some additional information on the board, some silkscreen. And I just realized my screw terminals are probably wider than 2.54, right? Let me just have I've got some screw terminals that I'm thinking of using for this. So yeah, they're definitely bigger than 2.54. I'm going to have to change. That footprint. The life of a maker never goes smooth, right? These are 5.54. So I need to change these down the bottom to 5.54. Let us figure that out. And this is good, right? Because it shows that you can come in here and make some changes and do all that sort of good stuff, right? Let's go back to the schematic. How can I change this, though? That's the question. Footprint. A designator, JP description. Okay, so that's on there. Footprint has... Okay. Let's place some new parts and then we can fix this, right? So... TSW 102. Let's find the part first, right? TSW SW-102. Okay, so what is my pitch? I wonder. No. No. Right, okay. Let's go for TSW-102. Okay. So we got to have a pitch of around 5. And these are in initial, they're not in integers, so the first number starts with a 1. So we got to go up till we get to the 5s. Okay, 5, 5.2. What is the actual pitch of this? No, it's not 5 by 5, that's for sure. See, I would have liked to have used a screw terminal. Connector. Terminals. What are these called? What are these screw terminals actually called? Other than screw terminals. So yeah, I think definitely this could do with a little bit of work in terms of usability. Certainly from a newbie's sort of perspective. Oh, hang on. What we got? I didn't realize there was more. Oh, hello. There was more. There was more, Captain. Okay, let's go 50 per page. So yeah, I think with more use, the familiarity of these components will definitely sort of it become easier using this tool. I think some of this is being unfamiliar. Let me find. Oh my god, I'm getting tired now. Screw terminal. That looks like pitch 5.08. Right, cool. Cool. Let's see if we can find this component in the library. No. But we know the pitch, 508. We don't have a 508 in here. So we go all 5.08 components with the pitch of that. It's 246 pages. Okay. So yeah, I think this could do a bit of work in terms of making it easier for a user to hunt down the component that they're looking for. Technically the case can, but yeah, but what do they fixed terminal block, that's what that's called. Let's see if that'll give me a good result on a search. Now I could go down into looking at trying to create my own footprint and all that sort of good stuff, but we're running out of time. Let's make sure I'm searching all components. Right, okay, that's fine. So this is Mauser, quite a large supplier. Okay, this is a slightly different product. We might be able to find this one. I've seen similar things in here. Oh, hello. Okay, I think we can make this work. Okay, so can I update this? No, I think I'm going to have to delete it. This is going to be interesting to see what this does. And where's the other 2-pin? There. Let's get rid of that. Okay. Let's go find him. Okay. Let me just check this PCB before I update it. What pin was 12 volts? Pin 1 was 12 volts. So I need to match that up. So let us select it, edit, and we're going to reflect y-axis. Okay. Let's see if this breaks things. It's got a good chance it could. Keep forgetting that's underneath. Okay. So let's update the net, and then we're going to just have to fix the traces a minute. And these are actually backwards. Okay. They're now crashing. What does the 3D look like? I've probably broken this completely now. Okay, well, they're facing the right way for starters, so that's good. Yeah, I'm going to have to odds this around, I think. Okay, so I tell you what I'm going to do. I'm going to select this component, and I'm going to rotate it. Oh. Yeah, right? Trying to select the whole thing, so... There we go. No! What? 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 What is this wizardry? Right, I'm going to get rid of this copper fill. Goodbye. You are the weakest link. What on earth is going on? Right, file. Save. Okay. I think I've bugged this out completely now. So I'm going to come all the way out to my workspace. I'm going to go back in the file and see if I can fix it. Oops. There's nothing like an idiot poking at software to make it not behave. There we go. Yay. Well, that was weird. Okay, I'm going to put it on the edge of the board with the intention of soldering it nice and low and then folding it over. I should have thought about that at the very, very beginning. Okay, let's fix these copper traces that I've just broken. So this is actually a really good demonstration of the software's ability to, handle making changes. I'm reasonably okay with this because the vast majority of what's going on is actually me being a complete and utter doofus, right? So let's align. Now the reality is, I'm in this example, I'm probably not going to install screw terminals. I'm probably going to solder a wire directly to the board. Copper Phil, that's my neighbor who's a police officer. Right, Dimitri? That's kind of funny. There's something going on here. The more tired I am, the funnier your jokes appear to be. But, just saying. Right, I want to move these now, right? So, for some reason, they wouldn't move then. There we go. So, I'm just eyeballing them to get them on. And now, what we're going to do is we're going to draw a trace, a 1mm trace in a second. Let's go here. Oh, what size is this? 0.4. Okay, so we'll go 0.4 here. That'll do. And we're going to go with a new trace width of 1. I'm here. And we still got the DRC to do again. Oh my gosh. Okay. Now, if I'm able to make a board that looks pretty good, being a complete and utter numbnuts, then I think that's not a bad result, right? Okay. We're going to fill for the zone. Bosh. Okay, traces are now popped. So we should be able to now do a DRC check. And I think we're pretty much there. I'm glad I caught that issue, though, because we're going to place an order in a second. There's 34 errors, clearance constraints. So this line here is not happy. Why? What's happened here again? This is this bottom trace again. This bottom trace is having a meltdown. Okay, it looks like this via has lost its nets for some reason. Is that because I changed the socket maybe? I don't know. The plugs. So VCC via. That's a VCC via. That's a VCC via. That's a MOSFET A. So all of my vias seem to have just taken a poop. Okay. Okay, so copper fill. Here we go. Pour this layer. Okay, that's all our grounds reinstated. Let's do our DRC check. We're getting close now. Okay, it says it got 18 errors. What on earth is 18 errors worth? Okay, we got a clearance constraint we need to fix. Okay, so that is text. So if I just hide this, I should be able to grab and move. My text is clashing. Okay, bring that top layer back in. Run the DRC. Something's going really screwy here because we're losing traces now. So I'm not going to save this. I'm going to come back out and come back in. So it's a little bit buggy. I think that's fair to say. Yeah, we've lost. We've lost. Oh, hang on. What have I done? I'm thinking I can turn these off, but it looks like they're. Is that deleting them? I thought this eyeball was to turn these on and off, right? No? Is that not what it does? Show all layers. Ah! Phew. User error. That was definitely a user error. Okay. We definitely have lost traces, though. We run the DRC. These could be old errors, right? 40 errors. Okay. I'm not entirely sure why that's doing what it's doing, but it is. So some of the traces, for some reason, have lost their parentage. Okay, I think what I'm going to do is I'm going to close my browser and I'm going to relaunch this because I think it's just having a moment. And if it is, then we'll call it quits at this point, and then we will dive into this separately. So let's see, what do we got here? Let's get back in and see whether or not just the refresh of the browser. I mean, it could be my browser, I guess. I don't know. So we'll probably look to log some bug tickets here to get this tool improved, because I think, to be honest with, there we go. That's looking much better. What happens when we run the DRC? Do we get the errors, or does it like is it happy now? Okay, there are 19 errors. Those things are back. All right. It's going to take some time to fix these. But unfortunately, I've been unable to get to a point where I can order the circuit boards. So I've gone out, I've come back in, and we've still got these weird errors, and it's progressively getting worse. I'm gonna try. Let me just quickly try a different browser. See whether or not we've got a browser issue. I'm going to use just Chrome. I was using the Brave browser. Okay, I'm just logging in. I just need to... Oh, it'd help if I type the right password in. All right. Okay. We are logged in, and I can jump over to the scene. Let's see if this single channel low voltage circuit works out. So I've got a different browser. Is the problem still there? So let's run our DRC check. And if it is, then there's something in the background kind of going a bit screwy. Yeah, there's something in the background going screwy. So we're going to be unable to resolve that issue this evening. But I'll reach out to the guys over at PCBX and see if we can have a look as to see why that did that. But on the surface, I think this is a really promising tool for makers. If we can get those bugs be gone, that would be really, really cool, right? So the bugs in terms of the changing of the think about this, Steve. Think. So changing of the parameters seems to throw these errors. So I might need to rip the traces up and reroute it, which would be a pain if this was a much bigger board. The other thing I think could do with some work is the search feature within the database to get your components in. That I found quite problematic. But on the upside, if they can fix that, all of these components is from their database of components that you can have manufactured, right? The manufacturer has in the manufacturing process. So if you wanted the board assembled by them, it's literally done. The bill of materials is done. And that's one of the things I'm working through with KiCad at the moment. That's a real headache. So if that could be fixed, that would be pretty awesome. But visually, this looks really good. But we just need to fix the holes, the mounting holes, and the vias. Yeah, I think I need to get that under control, right? So, right then, are there any questions from anybody in chat before we look? Yeah, exactly. Exactly. So yeah, it's good. Some way to go to fix these little niggles. I mean, it's a beta, all right? I just want to be very clear about this. It's a beta version, right? So we've got early access to a tool. There's a couple of bug fixes that I put in already, and that has been fixed. And they've been really quick to resolve the issues that I've logged with them. So I'm hopeful that this can be resolved, and we can get to the bottom of why there was a problem with the mounting holes and why we seem to lose the traces. That's kind of like, I don't get why that happened. So have we created islands? I don't think we did. It doesn't look like we did, but yeah, there's a way to go. So in summary, promising tool, not quite there, but it is a beta. Thank you so much, PCBX, for sponsoring this content and giving me the opportunity to try out a brand new tool and hopefully develop it into, with feedback, into a really, really useful tool for brand new makers. So if you like this video or stream, if you're here in the chat, please make sure you give it a thumbs up. If you're not already following, hit that subscribe button. And we'll be seeing some more content. We'll do a follow-up. We'll get a follow-up on this and possibly a produced video around creating a circuit board, why we saw some issues, and what's been done to fix it. So that's really, really cool. Gary, so if you go to the link in the description of this live stream, click on the link to PCBX. You can sign up for an account with PCBX. PCBX is a manufacturer of circuit boards. And depending on what EDA you use, if you output your manufacturing files and send them to PCBX, you can get your boards manufactured and get really high quality circuit boards coming back. If, however, you want to use the EDA, you just go into your workspace from PCBX, and I'll show you how to get there. If you guys want to give this a try for yourselves, so once you're in to your account at PCBX, hit the online EDA designer, and that brings you into your workspace where there are a bunch of example projects, and you can create your own files. You can import your own projects, like KiCad projects that you've already got on the go. That would be really cool, right? Especially if you want to build the bill of materials and get the board manufactured with all the components populated. So give a big thumbs up to PCBX. Give them a look to see whether or not they're something that you'll be interested in using. I definitely will be using their services in the very near future. So if there are no further questions, thanks everybody for hanging out in the live. I hope this gave you some value and you learned something around the challenges of a maker making circuit boards. Sometimes success, well, actually, sometimes failure teaches you more than success, right? It's only a failure when you give up. So until next time, have fun, be safe, and I will catch you in the next stream. Bye for now.